welcome to Environmental Science. I know the last video in this lesson wasn't working very well once you got up to a certain point, so I'm re-recording, and I'm going to take you through a couple slides. It's just eight slides or 9 slides, and kind of get an overview of the nature of science. Before I do that, I just wanted to touch on the central case that you should have already read, and it's called Fixing a Hole in the Sky. Some things that you want to keep in mind. You should know these things. If you don't, and you're hearing this for the first time, this might help make a little sense of that case study for you. But essentially, those 3 things are that ozone occurs naturally, and it's a molecule that can absorb harmful UV radiation. It can also deflect harmful UV radiation. So the ozone layer is a very important layer in the atmosphere, protects us from getting skin cancer and things like that, at least to a degree. Something else that is important to point out is that back in the 1970s, Molina and Rowland were the ones who discovered that these CFCs, which are carbofluorocarbons, they're chlorofluorocarbons. So there's chlorine, there's fluorine, and there's carbon. These were the molecules that were rapidly destroying the ozone layer in the stratosphere. So these CFCs were used as propellants in lots of different aerosols. So you may have heard, if you've heard anything about the ozone layer issues, former issues, they were in hairspray. And back in the 80s, if you've ever seen pictures of girls from the 80s, they usually had humongous big hair. So they were using lots and lots of the Aquanet and whatnot. And Aquanet and all the other aerosols at the time contained these CFCs. So these CFCs were being pulled up into the stratosphere and basically destroying this protective ozone layer. And down near the South Pole, we ended up with a big hole in the ozone layer. And so if you lived in southern Australia, you were at a much higher risk of skin cancer than anywhere else in the world if you're outside. These CFCs have been pretty much banned across the board, all over the world, and as a result, the ozone hole is actually improving. It's getting better. It's not as big as it once was, and they expect that the ozone layer will completely repair itself by 2050. So a few years to go on that one, about 38 years to go. But in another 38 years, we shouldn't even have to talk about the ozone layer as an issue, but we can certainly talk about it as something that happened in our past. And as a result of our changing our approach to manufacturing certain products, we were able to resolve that potential catastrophe. So there's a little talk about it there if you want to read over that and give it some thought. It's good to think about. But let's get into the nature of science. As it says here, the word science means knowledge. It's a Latin derivative. Pardon me while the phone goes off. But it's a derivative from Latin, the word scientia. And again, that means knowledge. So science is the study of knowledge. So let's look at what science is and what it is not. Science tries to be very black and white, but you may find or may think or may feel like there's some gray areas, and I think there tends to be. But science really is an approach to studying the natural world. It tries to be very organized and tries to be methodical in its approach in order to rule out other possibilities. Because when we're doing experiments and things like that, in order to know what the cause is of an effect that we've observed, we need to eliminate other possibilities, other possible causes, and focus on just one particular cause. These would be what we call variables when we're doing experiments. So you should be familiar with that term, variable. If you're not, you will be within another week or so. But science basically assumes, now here's where we get some gray area, it assumes that the natural world functions according to all these rules that never change. So there's an assumption being made. As far as we can tell, these rules don't ever change. Since they haven't changed in our history, we then apply that perception of unchangeability to history and make the assumption that what holds true, seems to hold true now, held true in the past and will hold true in the future. One thing science doesn't deal with is the supernatural, although there's lots and lots of shows on now where they're, ghost hunters and whatnot going after the supernatural, and they're trying to do it in a methodical way, trying to eliminate other possibilities as to what these phenomena are being caused by. And so in that sense, science actually does deal with the supernatural, but it doesn't like to allow for supernatural explanations. It wants to see natural cause and effect, typically. But there are definitely some fringe areas of science that do work and deal with the supernatural. So I would not say that we can completely rule out the supernatural when it comes to science. In fact, personally, I don't rule it out at all. Science relies on evidence from measurements and observations. So in dealing with the supernatural, these ghost hunters and so forth are really trying to build evidence based on measurements that they make and observations that they make. They try to measure heat and light sources and different masses of molecules and just some weird things that they're able to measure that would indicate some kind of paranormal activity or what have you. This is an interesting statement. It's because we get a lot of this sense that it's very finite and it's this way and it's no other way, yet there's terms being used like assumes and relies on. So it's kind of like almost a contradiction, like science relies on evidence, yet it makes assumptions. So that's where there begins to be some allowance for gray areas when it comes to the sciences. And lastly here, scientific ideas are supported rather than proven. So we don't say, well, we proved this by doing this experiment. We more so say we can support this conclusion based on the data that we've gathered and analyzed. Okay, so we don't really prove anything in science. We don't. Of course, we say we don't accept things and don't believe in things, and again, gets back to that making assumptions, particularly when it comes to what we would call or refer to as historical science, science that happened long before there was anybody around to observe it. So we have to make all these assumptions and, in a sense, jump to some conclusions and believe that that's what happened because we can't prove it with measurements and observations. So take all this with a grain of salt, but in large part today, science today that doesn't really need to base itself on historical science does try to stick with real evidence and measurements. So we get into like pharmaceuticals and genetics and things like that. We try to look at real evidence, measurements, and observations that we can make when we combine certain molecules and proteins and things like that and see what happens. So much of science is truly based on evidence from measurements and observations. But there are some areas of science that do make assumptions that require us to accept or believe certain things, certain rules and guidelines and so forth. So enough of that. Let's move on to the actual process of science. And of course, the most important part of science, and I think this is the most important part of education too, is asking questions. So I want you guys asking questions this year. Ask questions about the content, ask questions about science. If you see some connection between something you read and something else you know about, have heard about, or whatever, and you're wondering what the connection is, certainly ask, and I'll try to answer those. But we ask questions, we make observations, we see things happen, and we're like, why did that happen? So then we go and try to find evidence, and then we share these ideas that we come up with, our conclusions based on the evidence that we've gathered, and then we can maybe develop some experiments to test our assumptions and conclusions and analyze our results and see if we were on the right track. This is not a linear process. There's not really a step 1, step 2, step 3, step 4, although we usually start with the question asking or the observation and then the question asking, and then start doing some gathering of data, some experimental design, and then interpretation of data. However, even though we tend to go in that order, once we get to the data analysis, the process can loop back on itself and take us down a different path of thought. So it isn't completely linear, although it's somewhat linear. It at least starts out in a linear fashion and then can kind of loop back on itself and kind of get into a vicious cycle until we've narrowed down the possibilities. Okay? Hopefully that makes sense to you. So it's a very dynamic and creative process, and because it's creative and it's dynamic, it can be very exciting. So if you're not a big fan of science, hopefully you will look at it as this idea of exploration and discovery, which is what we're going to talk about here. So a lot of the investigations that we're going to read about this year, some of those investigations that we're going to do ourselves, they basically all start with observing a phenomena. And a phenomena is anything that occurs in nature that we can't explain right away, or at least we're not sure how to explain it, but we want to be able to explain it, so then we begin making more observations. We can begin to do this with different instruments. We can even do it by reading other scientific literature, and that's a lot of what you're going to do this year. You're going to be reading your textbook, or you're going to be reading articles, you're going to be reading case studies, and all of this would be considered scientific literature. And so a lot of scientists, because they're sharing their information, help other scientists. So I might be studying one thing, but I don't have to do some of the experiments because some of them have already been done. So I can take what another scientist has done and kind of move it forward from what they've done by doing some additional experimentations that I want to do to explain some other phenomena that are related to what the other scientists had done. Observations, they can be things that happen unexpectedly. For instance, Isaac Newton saw an apple fall out of a tree, so they say. I don't think that's entirely true, but he's like, wonder why that apple fell. I wonder if the apple falls every time that it is released by the tree. And so he began making additional observations after that surprise apple fall, and was able to put some things together and come up with this idea of gravity, right? And a lot of times these observations, especially when they're unexpected, lead us to other questions. All right? And once they lead us to other questions, we can begin talking to other folks, other scientists and colleagues, other students, and start trying to kind of discern and figure out what's going on. Of course, we're going to be writing lots of hypotheses this year. Well, maybe not so much in this class. We do a lot of that in biology. But hypotheses essentially are an attempt to answer the questions that we have. And it has to be a testable idea in order to be a valid hypothesis. A hypothesis will either attempt to explain a phenomenon or answer a scientific question. When we write a hypothesis, this can generate some predictions. We can basically predict what's going to take place. We can check them against models, and we can do direct observation and determine if the observation or the hypothesis is true, and those kinds of things. and our hypothesis can either be supported or rejected by the data. So these are things that are important when writing a hypothesis. First of all, again, it has to explain a phenomenon or answer whatever our scientific question is. It has to be able to generate predictions that we can then check using models or direct observation, and it also has to be provable or disprovable. Okay? In fact, technically, it only has to be disprovable. It's a hypothesis, something that can be disproven. Okay? When it is disproven, it could prompt new hypotheses. Okay, so once we develop our hypotheses, then we begin gathering data. And this is how we test our predictions. We gather evidence, basically, and this generates our data that we gather. If the data we gather matches up with our predictions, then we could say that that data supports our hypothesis. Remember, we support a hypothesis, we don't prove or believe it, right? If the data doesn't match the predictions, though, then we have to reject that hypothesis, and then we write a new one. So this data can come from either experiments that we do, or basically just doing observational studies. The picture here that you see of a scientist and the seagulls, she's actually doing a study of the migratory patterns of seagulls, and so she's using observational study to gather data. Okay, so that's pretty much it for lesson 1.2. If you like, you can read through that section in the book, or just kind of skim over it, pull out any other information that might be important or interesting to you, and answer the questions at the end of this lesson. Okay, thank you.